Hi, it's Paul Andersen, and welcome to Disciplinary Core Idea PS2C. This is on stability and instability in physical systems. Remember, a system can be as large as our solar system, but it could be as small as this hourglass clock right here, which is in a pretty stable state. But if I were to flip it upside down, sand would start pouring through it until it returned to a more stable state. And so that's what this video is really about. If we look at a system is in its current state based on all the interactions going on around it or with it. And so the stability or instability of that system is based on the sum total of all of those interactions. And so we can have stable systems like this pendulum hanging from the ceiling. We could have objects or systems that are static. In other words, they look stable, but they're relatively unstable. This ball is ready to slide down this hill. We could have systems that look unstable or are changing, but they have stable cycles, like the moon moving around the Earth. And we can even have systems that are stable even though they're changing rates. And so this person right here might be 77 kilograms, but that's based on eating, and waste that's coming out of them over a long period of time. Even though their weight may remain the same, they have varying changing rates that are coming in and out. And so how do we maintain stability? So how do we maintain, for example, an internal body temperature of 98.6? We use something called a feedback loop. In other words, if it gets too hot inside our body, we're going to start to sweat. And as that sweat evaporates, it's going to pull heat away with it. That's going to lower our temperature. Let's say we start to get too cold, we're going to start to shiver, and that shivering of the muscles generates heat, and that's going to increase the temperature. What's interesting about this system here is it requires energy. In order for us to maintain a stable temperature on the inside, it requires a huge amount of energy. And if we take away that energy, we take away that feedback loop, it's going to return to a more stable, naturally stable state. And so an example of that, let's say we have two objects, one is hot and one is cold. That's unstable at this point, especially when we put them next to each other. We're going to have movement of all of the molecules inside it, and it's going to eventually return to a more stable state. They're both going to be warm. And so over time in our universe, things tend to return to a more stable state over time. And so sometimes systems are too complex. And so if we're looking at the molecules that are moving around in those objects that are warm or cold, it's impossible for us to predict the motion of all of those molecules. They're all moving, they're bouncing, they're hitting each other. And so the future at this point is unpredictable in a system that's incredibly complex. But what we can do is we can make predictions about the average future. In other words, when we're measuring the temperature of an object, what we're really looking at is the average molecular motion. Or if we're measuring a reaction rate, we don't know when all of those specific atoms are going to combine and break apart, but we do know what's going to be the average rate of chemical change. And so how do you teach this in schools? Well, in kindergarten and first grade, you want to talk about objects moving and why objects are moving or not moving. And so if we watch this basketball right here as it moves across the screen, you might ask kids like, why is it moving? And the good answer might be that it's being pushed. And so we could start to look at all the pushes and the pulls. Maybe the basketball is being pulled in this direction. Maybe we have gravity pulling it down and friction pushing back on it. And so I can imagine in an elementary class, if you have an object and a bunch of ropes around it and we're all pulling in different directions, it's the sum of all of those interactions which are going to cause that motion of the object. And a really good question might be, let's say we have a basketball that's not moving. Are there any interactions on it? Is anything pushing on it? Well, they hopefully start to understand that you could have a bunch of things pulling on it or pushing on it, but if they all add up to each other, then you're not going to have movement. And so even though there's no movement, doesn't mean that there's no forces or no interactions on it. As you move into the upper elementary grades, you want to start talking about the forces, all of the forces they can identify within a system. And so if we're looking at this pendulum right here, what are the forces acting on that pendulum? It's not moving, but you could ask them, what are some forces acting on it? Well, one would be gravity pushing down, and then it's not going down, so there must be another force, and that would be the tension moving up. If we were to look at this ball now on the top of this pyramid, what are the forces acting on that? Well, they could see gravity, but there's no force holding it there, so if we let it go, it's just going to move down. Or you could even ask them, the Earth and the Moon, as the moon orbits around the Earth, what are some of the forces and interactions between those two? Well, they might think, I don't know what there is, but you know that there's got to be a gravitational force, otherwise the moon would just fly off into space. And so this is a good place to start in elementary, and then you also want to get at this idea that sometimes systems will remain the same even though things coming in and out of it are going to be changing. And so this is Lake Mead. And so Lake Mead seems to be stable. This is a picture taken, a satellite image of that. But you could say, is there anything coming into a reservoir like this? And is there anything going out? And they'll quickly realize that the Colorado River is flowing into it. And then a lot of water is flowing out of it. And if the sum amount of those coming in and those going out are equal, then it's going to remain stable, even though there are different rates coming in and out. Also, you want to get to the idea of speed. And so if we look at a flower like this that is flowering, you might say this is a pretty stable system, but they have to realize that speed is putting us at one point in time. And so if we speed it up a little bit and do a little bit of time-lapse photography, now they wouldn't say that this is stable at all. And so certain things occur so slow that we can't see them, and so fast that we can't see them as well. And then a lot of those interactions, so if we're talking about something fast, as hot touches cold, there's going to be a transfer of energy. That's going to be heat between the hot and the cold object. But the amount of that heat is going to be based on what those objects are made up of. And so a really good thing I do in class is ask the students to hold on to the metal on their desk and then hold on to the top of their desk. And I ask them, which one of these is warmer? And they'll always say the desk is warmer because the metal on my desk is cold. And the right answer is that they both are the same temperature. They're room temperature. And so why does the metal feel colder? It's what it's made up of. It's going to allow more of that heat to be lost quickly to your or hand, or vice versa. Next, as you get into middle school, you want to talk about stable and unstable systems. And now would be the time where you could talk about feedback loops. In other words, stable systems are going to stay the same as long as we have constant feedback going into it. And so a great example in us is going to be the temperature inside our body is going to stay the same because as we get warm, we're going to start to sweat, and as we get cold, we start to shiver. But you might ask them to apply that in their classroom. And so where do we see a stable system in their classroom? Well, the temperature in the classroom stays the same. And why is that? Well, as the temperature starts to get too hot, it's going to turn off the heater. And maybe if you're lucky enough, you've got air conditioning, it's going to cool it down. And likewise, when it gets too cold, then it's going to start to increase the heat. Now, turn that heater on. And so what happens if we remove all of that energy? It's going to quickly go to a relatively stable environment. It's going to be the same temperature as its surroundings or its environment. And then as you get to high school, you want to talk about this idea that sometimes the future is unpredictable. In other words, in real complex systems, and two great examples of that are when we're looking at temperature and the average, the movement of all the molecules inside it which cause that temperature, and then also in chemical reactions. And they should understand that even though we can't make great predictions about all the individual parts of that system, we can make predictions about the average. And so what is temperature? Temperature really is just an average of the molecular motion of all the molecules inside that. And so that's where you want to get to when we get to high school. Those are systems. They're sometimes stable, sometimes unstable. If we pull out that energy, it's eventually going to be stable over time. And I hope that was helpful.